Saxon Algebra 2, Lesson 118. As you may recall, I explained yesterday, I'm changing the order of things a bit in the lineup here for the last week of classes. Yesterday we covered 117 and 119 together. Today I'm covering 118 with a dash of 122 thrown in. I'm not putting this in the title because we're not going to go and do any problems from 122, but I just wanted you to know that we are getting bits and pieces of those lessons that I'm skipping mixed in. This is another area where I don't know why John did things the way that he did, because the information that's in lesson 122 is absolutely vital for you to understand in order to do 118. So John, don't worry, buddy. I got you covered. You got your lessons out of order, but it's okay. We're fixing it. This lesson begins with a chart. Yay, I love charts. Draw something that looks like this. Skinny row at the top. 3 columns, 2 wider, 1's a little bit skinnier. Now we're going to divide these into additional rows. I'm going to make this into 3 rows, and the middle one's going to be a little bit fatter. Okay, that's what I'm looking for. You'll remember that for quite some time now, I have been trying to shove into your brain something that we call the rules for exponents. You're groaning. It's okay. I'm not. My feelings aren't hurt. These are some simple rules that we have been talking about since the fall of Algebra 1 year, and yet I've never put another column over here, have I? It's always just been like this, but we're going to add something to that. So let's just recap our rules for exponents. We have a product rule, and that one tells us that if we're multiplying 2 matching bases that have exponents, we can add those exponents. We have something called the quotient rule. I like to call it the quotient rule, but that's not how you really say it. And that tells us if we're dividing, we can subtract the exponents. And the last one is called the power rule. And that one says if you're raising a base with 1 power to a higher power, you can multiply. All right, we've seen these, we've used these, blah, 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 blah. I've tested you on them. That's fine. But remember how I told you that exponents and logarithms are 2 ways of saying the same thing? Sometimes I think of them, if the exponents are a t-shirt, you turn the t-shirt inside out, and that's what logarithms are. They're familiar, they're the same, they're a little bit disorienting, right? Because the seams are showing on the t-shirt and the tag's flipping out. But they are really the very same thing. So what we have are laws for logarithms, and I'm just going to write logs. I'm going to abbreviate that. Now, I don't know where the exponents were when they were handing out titles, because I think having laws for logarithms sounds way more impressive than just rules. But despite the relative difference in the words, they're the same, because look what happens. If you're multiplying in the argument, you can make them separate and add them. Now, this looks a little different than that. I'll agree with that. But multiplying goes with addition. Multiplying goes with addition. It doesn't look exactly the same because the t-shirt's inside out, if that makes any sense to you. But multiplying goes with addition. Therefore, when we go down here, subtraction goes with division. I think I said adding goes with multiplication. Multiplication goes with adding. And here we have division going with subtraction, division going with subtraction. In the rules for exponents, we tend to always move from this direction toward this. In the laws for logs, we tend to go back and forth a little bit more, just so you know. You'll see that, but we go back and forth a little more. So multiplying goes with addition, division goes with subtraction. Those parallel pretty closely. This next one is a little harder to see, but it's so much fun to use. If you have a log where this is raised to a power, you can take that down. You can take the exponent down and make it a coefficient on the front. What? Right? This exponent can come down and be popped here as a coefficient, or if you have it in this form, you can take that little x and just pop him up as an exponent on top of the m. Whoa, that's crazy, right? This one, again, it doesn't translate as well, I don't think, but I guess you take the exponent and you're multiplying, and it's harder to use words to describe how those are the same, but this one is super fun to use. So what we're going to do is solve a few log equations. We don't need calculators. In this one, I want to say this about logs. Some problems are more focused on solving. That's what we have been doing. Those require the use of a calculator. Some log problems are more focused on simplifying. And in these, we don't tend to use a calculator, we use the laws of logs. Okay? In these, we need the bases of 10 or e, because those are the ones we have the calculator for, right? These, we can use any random base because we're not going to be solving them. We don't need to take them to our calculator. I'm underlining those so you can see what I mean. These, as long as they match, we're fine. We don't have to worry about it. All right, let's take a look at these problems. There are three. A perfect number. Example 118.1. Solve. If you were doing this as part of your homework, you wouldn't have to write this all out. I'll show you at the end what I would do. Okay, as I write it down, my head starts to spin because I see that base 3, what the heck are we going to do about that? Well, guess what? Nothing, because this is a problem, like I said, where we're simplifying rather than solving. So we don't need to use the calculator. We're going to rely on our laws of logs, and any base is fine. It is important that the base matches, but they do. They're all log 3. So don't let that worry you. We're now going to ignore the base 3. It doesn't matter. I've got another copy of my law of logs here, so we can refer to those. But we look at this and we go, okay, we're adding 2 logs. Wasn't there something about when you're adding 2 logs? So we go back and we look at our chart here, and we go, oh, it's right here. If you're adding 2 logs, you can multiply. We call this part the argument. We can turn them into a single log expression and multiply the arguments. So the arguments are x plus 7 and 2. So I'm going to combine these into a single expression. The log 3, fine, that just stays the same. X plus 7 times 2. This is all now one big argument, and it's equal to log 320. Now I'm going to tell you something magical and fun. If you have a log expression where log equals log, like we do here, right? Here it was log plus log equals log. But here we just have log equals log. This is delightful. When you get your equation rearranged to a point where you have log equals log, as we do here, as we did not have here. This is log plus log equals log. This is log equals log. We can simply lift these arguments off and solve. So what I'm going to do is say that x plus 7 times 2. Now, that feels a little backwards to me, the way it's written here, but that's fine. We can fix that in a minute. Equals 20. Now we just solve this, and look what precious, cute little algebra it is, right? So this is fabulous news to us as we work this type of problem. So now we are getting, let's see, I'll distribute here. 2x plus 14 equals 20. I'll subtract the 14. 2x equals 6. And we get for our final answer that x equals 3. Now, just to clarify and be like math nerd specific, technically we are solving this problem, but we're not solving the log expressions themselves. We're just solving for an unknown. We're solving for x. That's why we don't need calculators, and we didn't, push any buttons in the calculator that had to do with natural log or base 10 or anything like that. We're solving for an unknown, but we're not solving the log expressions, if that makes any sense to you. But this is this beautiful process where if we can reduce both sides to being a single log expression, then we can lift the arguments and solve. Happy days. Okay, let's do the next one. And no spoilers, but notice that the first problem used the first rule. Oh, and there's 3 problems. Oh, ready? Here comes the next one. Solve. Log of 14? That doesn't sound like anything I've got in my calculator, but my brain goes, okay, just make sure they all match. All right, I see that they do, so now I don't worry about that 14 anymore. As long as they match, then I can use my laws of logarithms, and I don't have to worry about their weirdness. So I see that this side is simplified to 1 log expression. I want to do that thing where I lift off the arguments, but I have to make this into 1 expression. Right now it's 2. So I glance at my beautiful laws of logs, and I go, oh, look, I'm subtracting in this situation, aren't I? Log minus log, that's this. So I can take those arguments and I can combine them into an argument where there's division. So that's going to be like this, log of 14. Now it'll be this one, and I'm going to keep them in parentheses, over this one equals log 14/7. So I use the quotient law for logarithms to create this expression, because I'm subtracting here, so that means I can divide them. Now I've got log equals log, and I can pop them off. X plus 3 over x minus 3 equals 7. I feel comfortable taking the parentheses off here. I'm going to cross multiply. I'll get x plus 3 equals 7 times the quantity x minus 3. I'll distribute. X plus 3 equals 7x minus 21. Easy stuff, right? At this point, we're fine. I'm gonna add 21. I'm gonna swim the plain numbers this way, and then I'll send the x's that way. I don't know why I did it in 2 rows, I just did. That cancels, and we get 24 equals 6x. Divide both sides by 6, x equals 4. That's the right answer. Now, again, let me say, it's true, we solved, but we didn't solve the log, we just solved for an unknown in a log equation. So that's why we're still on this side of the chart, and that's why we're relying on the law of logs and not worrying about the bases. Okay, one more. I wonder which law of logarithms we'll use this time. So mysterious. Example 118.3. Solve. Whoa, that's our first side of our equation. I don't like this. And a letter for the base? What? But I stay calm. And I notice that this side matches. And I go, okay, fine. It's fine. Now, I don't like this coefficient because as long as there is a coefficient here, I can't lift the arguments off. I can't just write x equals 64 because then I would be losing that information. But luckily, we've got this pattern right in front of us and we go, oh, look what we're gonna do. We're gonna take that 3, we're gonna pop it up as an exponent on the m, then we'll be able to take the log of both sides. Or that's not the right words. We'll be able to pop off the arguments. So this I'm rewriting as log bx to the 3rd equals log b 64th. Taking the log of both sides is something different that we're gonna do next year. So those words don't really work. Okay, now I've got it just the way I want it, and I can just take the arguments off. X to the 3rd equals 64. What number times itself 3 times is 64? Well, you know what it is, and so do I. Let's not make a mystery out of it. Right? Again, we solved for an unknown, but we didn't have to solve these log values. We didn't have to find values for the logs. Okay, that is the end of lesson 18. Obviously, this is super important. Write it in your notes. If you have not kept up a list of all your different formulas in a special, a book or a couple pieces of paper or something that you can easily carry forward to next year, now is a great time to work on that before the final. Remember, the final is coming end of May. This is not very far away, you guys. This is like next week. So get your formulas in order. Make sure you're memorizing things. We're done with lesson 118. Okay? Only do the homework for 118. Don't do anything for 122. I just wanted you to know that these laws of logs are actually shown in lesson 122, which is weird. It's kind of out of order, but whatever. So yeah, 2 more to go. Thank you. Goodbye.